In this lesson, we'll cover Unit 4, Acquisition 4 on intermolecular forces. Before we talk about what intermolecular forces are, let's talk about what they're not. So we have something called intramolecular forces. That prefix intra means within. So intramolecular forces are the attractive forces within a molecule. Your intramolecular forces are our bonds. So if I have a molecule of water, that covalent bond that is holding hydrogen and oxygen together is an intramolecular force. What we're going to focus on for this module are intermolecular forces. Intra means within, inter means between. So when we talk about intermolecular forces, which I'm going to abbreviate IMF, these are the attractive forces that exist between molecules. So let's draw a picture so we can show the difference. Let's say I had two water molecules. When we're talking about intramolecular forces, these are my intramolecular forces. Same thing here and here. These are intramolecular. That covalent bond that is holding hydrogen to oxygen is an intramolecular force. Well, if I have like a beaker of water, there are tons of water molecules in that beaker, and those water molecules are being held together by something called an intermolecular force. And we're going to see that the reason that these intermolecular forces happen is due to attraction of opposite charges. In this case, water is a polar molecule. Oxygen gets the partial negative, whereas hydrogens are partial positive. And that opposition of charge is going to attract these molecules, and that is going to hold them together. Last thing about intermolecular forces before we get down into looking at the types. Intermolecular forces help determine the state of matter, and we're also going to see physical properties of the substance. So let's say I had a few Erlenmeyer flasks. If I had a solid in this first flask, we're going to see that the solid molecules are going to be packed together tightly. The reason that as a solid those molecules are going to be packed tightly together is because they have a very strong intermolecular force. So remember, intermolecular forces attract two molecules together. The stronger the force, the tighter those molecules get pulled in together. If we were to have a flask of a liquid, those molecules are going to be a little bit farther apart. So again, as that intermolecular force increases, those molecules get pulled tighter together like a solid. If I were to have a gas, these are going to have the weakest intermolecular force, which means we're going to have the greatest distance between those particles. So stronger intermolecular forces are going to pull those molecules in closer together like a solid. If we have a really weak intermolecular force, those molecules are going to be much more spread out. There'll be much more space between them. So let's get into the types of intermolecular forces. First one, London dispersion forces, or sometimes called just dispersion forces. I like to abbreviate these LDF. These are the weakest intermolecular force. So you'll have to be able to rank some intermolecular forces by their strength. London dispersion are going to be the weakest. All compounds have London dispersion forces. So this one should be automatic. If you see a question that says list all of the intermolecular forces acting on a molecule, automatically put LDF. Every single molecule has some LDF. So why? And we're going to draw a picture, so stay with me for a little bit, and once we draw a picture, hopefully it's going to make a little bit more sense. So we know that electrons are constantly moving. And let's say at a particular moment, one part of the molecule might be more negative due to an asymmetrical distribution of electrons. So we know that electrons are constantly moving within the electron cloud. And then let's say at a moment in time, part of that molecule becomes more negative because of the distribution of electrons. So let's say this happens in two neighboring molecules. Well, what happens is that oppositely charged molecules momentarily attract. And when this happens, we call this either an induced or a momentary dipole. So let's draw some pictures to kind of explain what's going on. So let's say this is my nucleus. And out here in the electron cloud, I just have 3 electrons. So what happens is these electrons are going to be moving in the electron cloud orbiting the nucleus, moving around the nucleus within their orbitals. So let's say as they're moving at one point in time, we have an asymmetrical distribution of electrons. All of the electrons end up on this side of the atom. Or the side of the molecule, I should say. That is going to induce a partial negative charge because all of the negative charges are on one side. There are less electrons or no electrons on this side, so this side is going to be partial positive. If this happens with a neighboring molecule, we can have an intermolecular force occurring here. Because opposites are going to attract. That momentarily negative pole of the first molecule can be attracted to a positive pole of another molecule. So the reason that this one is the weakest is because these electrons are constantly going to be moving. So they might momentarily attract, but as soon as those electrons move, that attraction is going to break and the new ones are going to form. So since this depends on the arrangement of electrons and electrons are constantly moving, this is going to be a very weak attraction. The last important thing to know about London dispersion forces. If the molecule is nonpolar, it is the only intermolecular force. So if your molecule is overall nonpolar, the only intermolecular force that will hold together neighboring molecules will be LDF, those dispersion forces. Second type, dipole-dipole. These are medium strength. Stronger than LDF, but they're not the strongest type. These are medium strength forces. These occur between polar molecules. Polar molecules have a permanent dipole. So dipole-dipole, 2 molecules with a permanent dipole attracting to one another. Polar molecules always have a partial positive pole and a partial negative pole. So this is not a momentary dipole. We would call this a permanent dipole. An example of a dipole-dipole interaction. The bond between hydrogen and chlorine is a polar bond. Chlorine is more electronegative, so it has a greater tendency to attract those shared electrons. So chlorine would get the partial negative and hydrogen would get a partial positive. This molecule is always polar due to the difference in electronegativity. It does not depend on the arrangement of the electrons. I will always have a negative pole and I will always have a positive pole. So again, those opposites are going to attract. The partial negative chlorine of one molecule will attract the partial positive hydrogen of another molecule, and this would be my intermolecular force. This one is going to be stronger because it doesn't depend on the arrangement of the electrons. These poles are permanent. A molecule that has dipole-dipole interactions will also have some LDF forces because they have electrons. So we could still have an asymmetrical distribution of electrons causing some London dispersion forces. 2 down, 2 to go. 3. Hydrogen bonding. We're increasing in strength, so this is a very strong intermolecular force. It is stronger than dipole-dipole. Hydrogen bonding is a type of dipole-dipole force. It is a special dipole-dipole force that occurs between hydrogen, hence the name, and either fluorine, oxygen, or nitrogen. The reason it is one of those 3 atoms is because it needs to be a small electronegative atom. So hydrogen bonding is going to occur between either hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. Lastly, ion dipole. This is our strongest intermolecular force. And the name tells you exactly what your ion dipole force is going to be. This is the force of attraction that exists between an ion and a polar molecule, something that has a permanent dipole. An example would be like sodium chloride dissolving in water. Let's say I had a beaker and we had some sodium chloride. Let's say purple is sodium. Sodium is positively charged. Pink is chlorine, or my chloride ions, those are negatively charged. So if I were to put water into this beaker, hydrogen has that partial positive charge. It is going to be attracted to the negatively charged ion. Oxygen has a partial negative charge. So the partial negative from oxygen is going to be attracted to the partial positive sodium. So we can have these attractions that exist between ionic compounds or ions and polar compounds. let's sum up strength. Weakest, LDF, followed by dipole, dipole, followed by hydrogen bonding, followed by ion dipole. These are my intermolecular forces. Intermolecular forces are going to be weaker than intra. So if you have to rank molecules by their strength, our intramolecular forces, ionic and covalent bonds, are going to be the strongest. Intramolecular is stronger than intermolecular. And then when comparing intermolecular, ion dipole is strongest, followed by hydrogen bonding, followed by dipole-dipole, followed by LDF. All right, last thing for today. What if you have multiple compounds that have the same intermolecular force? How can you rank them according to strength? Well, as the size of the molecule increases, the strength of the intermolecular force increases as well. Direct relationship. As your molecules get bigger, the intermolecular force gets stronger. Why? There's more electrons. More electrons to produce more dipoles. So think back to that picture we looked at for LDF. We have the electrons that are constantly moving. If we have that asymmetrical distribution of electrons, we can induce a dipole moment. Well, the more electrons you have, the more dipole moments we can have. The more dipole moments we have, the stronger that attraction is going to be. So like for example, let's say I had methane, ethane, and propane. So as I go down, the size increases. Well, also as I go down, the strength increases. Methane would have the weakest intermolecular forces. Propane would have the strongest intermolecular forces. All of these molecules have LDF, London dispersion. They are all nonpolar molecules. So how do we rank them? It goes by size. Smallest to largest, direct relationship, weakest to strongest.